This is a short video about forcing in these second order linear differential equations. So what we've seen so far is maybe a bunch of what are called free mechanical vibrations, goodness, that was hard to say, that are modeled by mx double prime plus bx prime plus kx equals 0. And so that word free, what's that adjective kind of telling me about as far as that math goes, is that there's a 0 on the right hand side. In other words, there's no external force that's acting on the system. And so what we're interested in is what if there is some kind of an external force acting on the system? So in that case, what we'll do is we'll just put that force on the right-hand side. So maybe that force is also some function of t. So what we've done so far is maybe we've had a couple different, real life examples to kind of conceptualize some of these mechanical vibrations. But to give you some examples, maybe this equation on the left-hand side, maybe that models like a bridge, say, or like maybe a tall building. And so what are some of the external forces that that bridge or that tall building experiences? Well, maybe some force from like wind, or maybe like an earthquake, say, or maybe some kind of like vibrations due to traffic that moves along that bridge. So those kinds of things are what this f of t could actually model. I'll say that in a second. So if I go down, another example that maybe we've seen besides these mass spring systems is an example of these RLC circuits. And I've given you a diagram of a pretty common one. And the new thing in this diagram, so R is the resistor, C is the capacitor, L is the inductor, and then I of t is the current. And the current is the first derivative of the charge at any particular time. So the new thing in this example is maybe this E of t. So maybe attached to this current, there's a battery, and this battery exerts an external force on that circuit. And so what we'll see is like, maybe that battery is a constant force, or maybe it's some kind of like a sinusoidal kind of force that's periodic. So how do we set up some differential equations from here? Well, we use some physics that you're not responsible necessarily for knowing, but Kirchhoff's law tells us how a lot of these things relate to each other. And so Kirchhoff's law immediately gives us the second order equation in Q. Remember, Q is the charge at any particular time. So it's saying that LQ double prime plus RQ prime plus 1 over CQ is equal to E of t. And on the left-hand side, that's the sum of what are called the voltage drops over each part of the circuit. If you differentiate that equation, though, you get a separate differential equation where how do you solve for the inductor? Or how do you solve for the current? And so that's how we can get a differential equation where, again, it models what the current's doing just by differentiating each term in that equation. But what I hope that you see is that whether it's a mass spring system, whether it's one of these RLC circuits, they have the exact same type of form. And on the right-hand side, again, there's just some kind of an external force being applied to our system. And so what are these things? These forcing kind of systems? There's just kind of a real-world application of non-homogeneous second-order linear differential equations. So again, real-world applications of some non-homogeneous equations here. And how do we solve those things? Maybe that would be good to write down. Well, the main method that we have to solve them, according to our textbook, is undetermined coefficients is a good way to solve. There are one or two other ways, undetermined coefficients. Another common way is called variation of parameters, and so that one's not covered as deeply in this particular textbook that we're looking at, but if you see one of these problems, undetermined coefficients is the way to go.